All right, let's get right into it. We are going deep, deep underwater to solve a fascinating engineering mystery. The case? A massive gas field that's completely invisible. And the goal is to figure out exactly what's going on inside it, using, well, nothing but pressure readings and 5 years of really messy data. This is a story about some serious digital detective work.
I mean, this is the big question, right? You've got this colossal natural resource, buried under kilometers of rock and water. You can't just send a camera down there. There's no way to take a direct measurement. So, how do you manage it? How do you have any idea how much is left, or even how it's behaving day to day?
So to set the scene, we're heading out into the Atlantic, just off the coast of Ireland. This is the location of our incredible undersea energy puzzle. The Corrib gas field is, to put it mildly, a really big deal. It's tucked away in this complex sandstone formation way down below the seabed. And it's not just big, it is critically important. I mean, at its peak, it was supplying more than half of all of Ireland's natural gas. That's huge. And just to give you a sense of the scale we're talking about, geologists estimated the total volume of gas down there was somewhere around 1.2 trillion cubic feet. It's an amount of energy that's honestly hard to even wrap your head around, all buried deep beneath the ocean. And here's where the puzzle really kicks into high gear. You've got 6 different wells, all pulling gas from this one single interconnected reservoir. So they're all affecting each other. They interfere. How on earth can engineers get a clear picture of the reservoir's health with so much going on at once? Well, since they can't see the reservoir, engineers have to learn to listen to it. The problem is, the reservoir doesn't exactly speak clearly. The clues it gives off are messy. So the main way they listen is by keeping a close eye on 2 things: the pressure in each well and the rate of the gas coming out. Now, in theory, the changes in these numbers over time should tell you everything you need to know. But, as we all know, theory and reality can be 2 very, very different things. This slide just lays it out so perfectly. In a perfect world, in a lab, you'd run one clean experiment. You'd produce gas at a single constant rate, no interruptions, and you'd get this beautiful, simple data. The reality at Corrib, it's the total opposite. This field has been producing for years. The rates are constantly going up and down, all 6 wells are stepping on each other's toes, and to top it all off, you've got annual maintenance shutdowns that throw even more noise into the data. It's a chaotic mess of signals. So, how do you find a clear signal in all that noise? Well, you need a special kind of forensic tool. You basically have to become a deconvolution detective. Deconvolution is the key to unlocking this whole thing. It's a really powerful mathematical technique that takes all that messy real-world data and translates it. It answers a simple question. If this well had been part of a perfect, clean lab experiment, what would its pressure data have looked like? It's like cleaning up a messy crime scene to find the one crucial piece of evidence underneath. But, and this is a big but, this tool is not a magic wand. The source material calls it an ill-posed inverse problem. Now, that's just a fancy way of saying it's incredibly tricky to use. Tiny little errors in the data you put in can lead to gigantic errors in the results you get out. It really requires an expert touch. And because it's so sensitive, the engineers couldn't just dump the data into some automatic program and hit go. Nope, they used a manual, interactive approach. You can almost picture a detective at a whiteboard, right? Sketching out a theory, looking at the evidence, erasing and redrawing piece by piece until their theory perfectly explains every single clue. This human-in-the-loop method was absolutely essential for a puzzle this complex. And it's a good thing they were so hands-on because, while they were deep in this process, they stumbled onto a huge breakthrough, a really surprising discovery that completely changed how they saw the entire problem. You see, at first, the problem seemed almost impossibly complicated. The assumption was that you had 6 wells, all talking over each other, all interfering with each other at the same time. Trying to mathematically separate those signals is just a nightmare. But here's the twist. After a few years, once the field came off its peak production, something amazing happened. The whole system just stabilized. The reservoir, almost like it was alive, dynamically divided itself up. Each of the 6 wells carved out its own little neighborhood, its own stable drainage compartment. And just like that, the constant interference between them, it basically just vanished. This insight was an absolute game changer. It meant they didn't have to solve one giant, tangled-up 6-well puzzle anymore. Instead, they could treat it as 6 smaller, much more manageable single-well puzzles. Suddenly, the case was solvable. So, armed with this brilliant new understanding, the engineers could finally get to work cracking the case.
They started applying their manual reconstruction technique to each of the 6 wells, one by one. And the process was incredibly methodical. First, they'd assume a clean response for a well. You can think of this as the detective's first hypothesis. Then, they'd use a computer to simulate what that well's pressure history should look like, based on that guess. Then they'd compare the simulation to the actual pressure data, see where it didn't line up, and then they'd manually tweak their hypothesis and run it all over again. They did this over and over and over, refining their model until the calculated pressure was a perfect match for the real-world data.
And once this was done for all 6 wells, they had their answers. The messy, chaotic data had been transformed into 6 clean, clear signals. And wow, did those signals tell a story.
You see, each of these reconstructed clean responses is, for all intents and purposes, a unique fingerprint. It's a dynamic signature that reveals incredibly detailed information about that specific well and the part of the reservoir it's connected to. And just like real fingerprints, no two were exactly alike. So by comparing these fingerprints, the full picture finally came into focus. For example, well P4, which is right at the top of the reservoir, turned out to have the smallest drainage area. Super surprising. Meanwhile, wells P3 and P6 up in the north are the absolute powerhouses with the highest productivity. The fingerprint for P2 clearly showed it's kind of boxed in by geological faults, which was hurting its performance. And P5? Oh, it seemed to be poorly connected to the rest of the field.
And this chart, this is just brilliant. It's the proof in the pudding. It compares how much gas each well actually produces with the size of its calculated drainage compartment. And look how closely they match. The wells that produce the most gas are connected to the biggest volumes of gas. This is the smoking gun that proved their theory about the reservoir dividing itself up was absolutely correct. And so after all that detective work, we arrive at the final number, the solution to the whole mystery. When they added up the volumes from all 6 unique fingerprints, the total connected gas volume came out to 1.06 trillion cubic feet. And this wasn't just another static estimate. This was a dynamic measurement, giving them a much more confident, precise understanding of their most important energy asset.
You know, this whole analysis is just an amazing testament to turning noise into knowledge. By taking 5 years of chaotic, messy operational data and transforming it into 6 distinct fingerprints, these engineers were able to read the hidden story of the Corrib field. And it really makes you wonder, right, with these kinds of detective techniques, how many other complex systems out there have incredible stories just waiting to be told?